I'd like to show a Nixie clock that I've just completed. This one's a bit different from the other two kits that I've assembled before. I completely hand-built this Nixie clock. So I took the proto board and the raw tubes and a bunch of junk box components I had lying around and some bits and pieces from years of previous experimentation with Nixie tubes and similar technologies, and I put together this clock. It's based on Ian Sparks' Arduino based Nixie clock that he has made open source on GitHub. So the code fits on a single 320 Atmega 328p microcontroller running at 16 megahertz, and he's got complete documentation on his firmware and has made that freely available. A very, very nice job on programming. He also sells a board that's functionally equivalent to the logic module here for a very reasonable price. But just for the challenge of it, I decided I wanted to try to reconstruct his design using my own components, just to kind of have a nice relaxing around the home project. So that's what I did, and it actually is working quite well. Now Ian's board, as sold, has a very small, highly efficient, high frequency voltage converter that converts 12 volts input source to the required 170 or 180 volts DC required by the Nixie tubes to fire. I did not want to include that since the parts were a bit complex. I didn't have the parts kicking around. So what I did instead is I took these two transformers here that are these old surplus line transformers for 120 volts AC, and I wired those back to back, and I used a couple of the additional windings on there to boost the output voltage. So it takes 120 volts in through the line cord, the white line cord there. It goes into the top or the upper transformer on the image you're seeing here. Then I've got the windings, which are the blue wires, cross-connected on the low voltage side. And then the outputs 120 volts AC back again. Now you may wonder, what's the point of that? Well, the point is it isolates the voltage, the high voltage, from the line, which would otherwise be extremely hazardous. So some old TVs were designed so that one of the ends of the line cord were directly connected to the chassis of the TV, which was extremely dangerous because depending how you had the plug plugged into the wall, the chassis of the TV could become hot in respect to ground, so very, very dangerous. The other advantage of using the transformers is the yellow wires are a low voltage tap that I can use to generate the low voltage 5 volts needed for the logic circuits. So if you look down on the board here, you can see those two large filter capacitors. Let me just switch it around. On the back, I've got two bridge rectifiers, a high voltage and a low voltage unit. So I feed the 120 volts, actually it's boosted a bit to about 130, line voltage isolated into this bridge rectifier. And then the capacitor peak detects that and generates approximately 180 to 190 volts unloaded DC, which supplies the voltage required by the Nixie tubes. So that is unregulated, but it's quite stable and it works extremely well. There's no current limiting or anything else in that. It just is the raw output from that filter capacitor. By the way, on Ian's high frequency, high voltage generator, he's got, like, I think a 2 microfarad cap for the filtering, which works great at the frequencies that he's driving it at. But this is 60 hertz in the US, and it requires almost a 200 microfarad capacitor to get equivalent filtering. I noticed I had a lot of 60 hertz flicker when viewed under fluorescent lighting on the neons until I upped the value of that capacitor. Now you can see there's a second bridge rectifier here, this black block. And again, that's almost the identical circuit. It peak detects the 8 volts AC coming in to about 12 volts and feeds that as input to a 7805 voltage regulator, which outputs then the 5 volts for the filtered 5 volts for the clock circuit for the for the generation stuff. So here you can see under this nest of wires, the large 28-pin chip here is the Atmega 328P, loaded up with Ian's code through an external programmer. There's a 16 megahertz crystal and the associated loading capacitors to provide the clock circuitry for that. And there's an old Russian from the 90s BCD to decimal output decoder that's designed for driving Nixies. So the function of this is to take a 4-bit input code, BCD or binary coded decimal input code, and depending on the value of that code, it grounds one of 10 lines, which then will create or produce one of 10 digits on one or more of these tubes. And I'll explain how that works exactly. Now, the reason we can get away with using only one decoder is that this is a multiplexed clock design, which means that only one digit at a time is being produced by the microcontroller, but 100 times a second the tube that's actually active is being switched in order 1 through 6 of the 6 available Nixie tubes. So at that 100 hertz rate, it appears that all the tubes are simultaneously lit, and it works extremely well. The brightness is quite good. Now, these opto-isolator chips, these little 4-pin devices here, there are 6 of those, 1 per tube, and they take a logic input on the 2 pins on the left through a 1K resistor, and on the right side they switch the high voltage to the tube that needs to be selected next at that 100 hertz rate. And it does that through a current limiting resistor that keeps the current down to a reasonable value. Now, the current is rather high on these, but because the duty cycle is very short and because we're switching these on and off at 100 hertz, the tubes are only seeing about 1/6 of their normal duty cycle if they were continuously lit. So the net effect is the brightness is the same even though we're driving the tubes very hard for a small amount of time. Now, a couple of additional things that Ian included that I've got wired on here through some flying leads. Ian made provisions for backlighting using an RGB LED. He had 1 per tube wired up on his through some external FETs to drive the higher current requirements of the multiple LEDs. In my case, I didn't have the correct LED, so what I did is I drove a single LED directly off of the pins using a 300 ohm current limiting resistor for each of the 3 colors, which works quite well for a single one, and it's well within the current capabilities of the output ports. I don't like the look of the backlit or underlit Nixie tubes with the RGB color effects. However, the LED does provide some important operating feedback on the clock. So I did think it was important to include that. So I do have 1 LED, and it looks nice. The second thing is this, as Ian calls it, LDR, or light-dependent resistor. It's a cadmium sulfide device, and when light hits it, the resistance varies depending on the intensity of the light, and this is used through one of the analog input ports on the microcontroller to control the relative brightness of both the display and optionally the LED as well. So that's wired up again through some flying leads connected to the board. I've got that just kind of tucked in here for now. There's an additional LED. I'm using a yellow LED at the moment. This is the seconds or the tick LED. These could be wired into sort of a traditional colon separator, but I just have a single LED here. This is driven by a PWM signal that varies the duty cycle to the power applied to the LED, and it pulses by going from bright to dim back to bright again at about 2 hertz rate, twice a second, along with the seconds count of the clock. So kind of a nice effect. This can be wired optionally through a high voltage transistor to drive a neon bulb. And I do have some nice old Russian neon tubes that I may ultimately do that with, but for the moment I have it just wired into the LED for testing purposes. Okay, the only other thing of interest, I think, in terms of the circuit is this DS3231 real-time clock module. I've used this on a number of my own clock projects in the past. This has a DS3231 real-time clock chip that keeps accurate time when the clock is turned off. It is temperature compensated, meaning that the temperature is actually taken by the chip and used to apply compensation to the oscillator circuit. So it's accurate probably to within a minute, a year. It's quite good. It also has a small I2C double EEPROM that can be used for data storage, which is the smaller chip on a separate I2C address, but I am not using that in this particular application. It does have a lithium battery on the back. I believe the module supplies charging current to this, but a lot of these modules don't come with a rechargeable battery, including this one. So it's a good idea to take the resistor off to disable the charging circuit, since the battery is not designed for it unless you have the special, I think it's an LR instead of a CR2032. So that's just how they come when you get the real cheap ones. I have not done that here, so it's something I need to look into. But it has connections for power, ground, and the SCL and the SDA I2C connections that go to a couple of pin headers again that are on the board. So all in all, that's it. So came out pretty nice. The form factor of the board is a bit bigger than Ian's, but of course it's not printed circuit. There's a lot of point-to-point wiring and other junk on there, but all in all, I'm real happy with the performance. So let's get right down to seeing what it looks like. So here is the clock before power is applied, which I'll do in a moment. And one other feature I didn't point out in the earlier segment was I do have a single push button which controls all of the settable features on the clock through a single button, which works pretty well. I found these little membrane keypads, a single SPST push button basically connected via a ribbon cable that plugs directly into a 2-pin header on the board, and these are real handy. They have a neat, because they have a self-adhesive pad on the back. So you can kind of stick them anywhere you want on the case of the clock and just cut a little slot or hole underneath the sticky pad. And they're very durable. They have good tactile feedback, and they do a good job without any noticeable bounce, probably due to the quality of the debouncing routine that Ian's included in the code. So there you have it. So let me go around and plug in the clock, and that will energize the 2 iron old school transformers that I showed you before, and generate the high voltage to the tubes, and then also start the clock going. I have it set to 12-hour mode right now, so it's displaying, well, it doesn't matter at this point, 9:06:47. And you can see that the little seconds LED here is pulsing, as I said. Now, in a brighter room, it looks nicer because the number of discrete pulse steps seems to be greater than when dimming is in effect, and the number of steps, or the coarseness of the steps or something, seems to be reduced a little bit. But it still looks good. Light in here, it's kind of stormy outside today, so the overhead light is not as bright as it could be. Let me reposition the LDR here to point toward the lights, try to get a little better brightness. It is brighter in brighter light for better visibility, and then at night, of course, it dims slightly. That's a bit better. If I put my finger over the LDR to simulate darkness, you can see that the display noticeably darkens. Now, I do have the dimming limited to a fairly high value here, so as to be able to get a little better visibility for testing, which I may put back to the default. When I take my finger away, you could probably see that the display did brighten up. Now, you can probably see a little bit of the flickering in the video. That's not evident in the actual human eye response to the clock. It's an artifact of that 100 hertz cycling rate, which is quite fast for a Nixie clock. It's quite a high rate. So Ian's got a very good interrupt service routine that drives that 100 hertz rate optimized for very good performance. So it just kind of basically sits there and counts off the time. Now you'll notice whenever a digit hits 10 or 0, it rolls back, or 9, it rolls back to 0 on the 10 count. Kind of a neat effect that Ian's included as an option here. So I have that turned on, and that affects all of the digits as they hit a roll over to the next decade count. So that's kind of cool. Also, there is a provision that you'll see run here in a few minutes. At the 9th minute of every 9 minutes and 15 seconds, a special cathode poisoning elimination or prevention routine will run. And what that does is it exercises all of the digits on all of the tubes for about 15 seconds at full brightness. And there it goes. So it has kind of a slot machine tumbling random kind of thing. And the purpose of that is to prevent the unused digits or the lesser used digits. For example, the digit here, the first one, is only really used for 1 in 12-hour mode and maybe for some special displays. So eventually what happens is the cathodes get poisoned by emissions from the active cathode, and they'll become dimmer, or in very bad cases will fail to light completely. And this tumbling routine basically just stops that from happening. So quite effective and makes kind of a nice visual display. There's kind of a neat feature that if the dimming function is all the way down, meaning lights are off in the room, that tumbling at full brightness on the 9th minute is suppressed so as not to be distracting in a dark room or while you're sleeping. So a very nice idea on Ian's part there. Little LED here provides basically just a little bit of a mood light. I have it set right now to respond to the dimmer. You can turn that off and have it at full brightness. You can lock the color mix to a certain mix of red, green, blue values on this LED. I have it set just to cycle very slowly through the different color modes, the different spectrum. So it gives kind of a nice, relaxing, low impact kind of effect. It does, however, have some kind of interesting capabilities for feedback, and you can see that when we go into the setting mode of the clock. In normal mode, before we do the settings, if you press the button once, you'll get the date in US format here. So it's July 13th, 2017. After 5 seconds, it returns to normal timekeeping. If I press it twice, it displays the temperature in Celsius, which is 25.25 degrees. The 31, I'm not sure what that is. It has something to do with the mode of the temperature display. I'm not sure why Ian doesn't suppress it, but it's kind of a weird format, but that's how it is. So it's 25.25 Celsius. So roughly room temperature right now. That temperature sensor is actually included in the little real-time clock here. It's used for the time compensation that I mentioned earlier, but it has a side effect of being able to be read. A disadvantage is that the board internally only updates that temperature every 65 seconds, I think, so it's very unresponsive, but it's not something you would normally look at. And the temperature of the components on the board tend to affect it, so it's not that great of a indicator of ambient temperature. So, use with caution, but it's better than nothing. There's some one-wire bus options out there. It's little sensors made by Dallas Semiconductor that offer perhaps a little bit better performance. If I hit the button 3 times, it gives a display of the LDR value, and you can see that kind of change as I wave my hand over it. That's kind of for diagnostic purposes to see what's up and if that's connected correctly. If I hit it 4 times, it displays the version number, which is 47. The 07, again, I'm not sure what that is. I think it's something to do with the mode of displaying the version number. Again, probably would be better to suppress it, but it's fine. It's not something that you look at all the time. Now I should mention Ian's got some code in here that drives the high voltage generator on his board. And at startup and continually it tries to adjust and regulate the voltage to some degree on the board. Now, since I'm using an external high voltage supply, none of those functions operate. However, it doesn't seem to interfere with anything, having those functions in the background. It seems pretty much to ignore it. I've got those connections on the microprocessor pretty much just left open at this point, and doesn't seem to have any ill effect at all. And in fact, Ian gave me some guidance that indicated that was not a concern. Now, to access the setting functions on the clock, it's necessary to press and hold the button for a little over 1 second, and that can be tricky to do. There it goes. And you can see that some digits are highlighted, some are not. And the LED here now is flashing this rather strobe-like white indicator that indicates by the number of blinks the mode, the software mode of the setting option that you're in. Now, that doesn't really relate to the numbers in the guide that much, but it's kind of more of a diagnostic function. You can actually count those blinks and refer to the code to find out what mode you're in if the manual was not up to date. As I was fiddling around with some new pre-release code, and I had to actually go back and look into the manual to find out what those blinks meant, because the numbering had changed a bit. So anyway, in this case, we're in the minute setting mode because the minutes are highlighted. If I press and hold for an additional second, we're in the hours setting mode. I'll press and hold it again for another second. Now we're back to minutes again. Let's see. Oh no, sorry, that was the date. So that was the day, that's the month, and this is the year indicated here. So there's literally, I think, about 45 different options. Now the actual setting options are indicated that have nothing to do with date and time, are indicated by a flashing 2-digit code on the right-hand side, which is different from the LED flashes here, which are the actual software code. So it is really not a correlation. I think these are number of flashes is 6 higher than the indicated code, 6 or 7. So it's a little inconsistent, but it makes sense if you understand what the developer has actually done. If I press and hold it again, we go to 1, which I think is the 12 or 24-hour display. So now a short press will toggle that from 1 to 0, and if I hold it down for a second and release, we're now in 24-hour mode, which you can't see other than the fact that we now have a 0 in front of the 9. Before that was suppressed in 12-hour mode due to a setting. So that's pretty much it. So a very nice clock. The multiplexing works well. There's not a trace of ghosting. I like the dimming function. I like the fact it's open source. There's a couple of modifications I'd like to make, including adding a Fahrenheit display rather than Celsius. So Ian has been quite generous in making that available for those who wish to kind of roll their own or play around with his creation, which I think is a very nice gesture on his part. I should mention that Ian makes I forget the number, ESP3366, it's a Wi-Fi module that's very popular with the Arduino crowd. And it takes the place of this 4-wire RTC module and actually adds a web interface into the clock that allows you to log in over a web browser on a computer and set all of the operating modes, the time, and to get various status information back from the clock. It also allows you to go out to an NTP or Network Time Protocol site on the web and set your clock from that. So you don't really need an RTC. So as long as you've got a good Wi-Fi connection, you'll have a very accurate clock. Now, even if you were to lose that, or even if I were to disconnect the real-time clock circuit, the clock will still run. It'll still try to keep time using the internal, the 16 megahertz clock oscillator on the Arduino, but that is extremely inaccurate, but it will keep a fairly coarse time running for a short amount of time while Wi-Fi is interrupted. So if you lose it, it won't interrupt your time, but it's good to be sure that's all working correctly. It's a little tricky getting that set up. Ian sells the setup for a real reasonable cost, but the Wi-Fi module requires level shifting from 3.3 volts to 5 volts and requires the capability of actually downloading another set of code that runs in the Wi-Fi module itself autonomously and provides the web server interface and the logic to interface with the setting circuits on the main Atmel processor. So a lot of work Ian's put into that, and it, from all accounts, works well. I may try to buy my own inexpensive Wi-Fi module and build a level shifter setup and everything, but you know, it's a little bit complex because you need a voltage regulator that operates at 3.3 volts, and then you need to come up with some level circuits. I've used some diodes in the past to accomplish that level shifting without any active components, and it may or may not work on the Wi-Fi module. Depends if there's pull-ups on the general purpose ports or not, whether that diode interface trick will work. So I may try it. It's worked with SD card readers and some other 3.3 volt devices I've used in the past. So anyway, very complete solution, and I encourage you to buy the module, which comes as a board without tubes or tube boards, so you still have to come up with some kind of mounting arrangement for your tubes. But you can hand wire these by soldering directly to the pins. I don't know if you can see this, but I should mention this. What I've done for my interface board is I purchased from OSH Park a PC board manufacturing service online from a publicly available design, these little INS-8-2 Russian Nixie tube interface boards. So the wire leads soldered to the board, but then it breaks it out on a standard pitch header, 5 on the front, 6 on the front, and 6 pins on the back, including the comma and the high voltage anode connection. Then I was able to take these and plug those directly into this prototyping board. And I actually had to use 2 boards with jumper wires going across them, and then checking to be sure the spacing was relatively the same. And then, because all of the digits of all of the boards are in parallel, I ran these jumper wires across to parallel all 6 in for each one of the digits. So there's what, 10, 11 actually with the decimal point. Decimal point's not being used here, but I guess I could use that for a digits pulsing display if I wanted to. In fact, I tried that, but it was very difficult to get the comma to stay lit with different resistor values when the dimming was in effect, so I kind of abandoned that whole idea. So I don't know that Ian sells the tube mounting options. I think he promotes more of a point-to-point wiring on the pins directly. But if you want to roll your own, that's certainly an option. Support is very good on the board. Ian also sells an all-in-one kit that has the tube mounting and everything all set. I don't think he had anything set up for these IN-8-2 tubes. They're set up for a more common Russian tube. What I like about these, though, is that the 5 on the tube is on some of the cheaper Russian tubes actually inverted and backwards 2. So they take a 2 and they flip it around so it's mirror imaged and then invert it. And it's supposed to look like a 5. To me, it looks awful, so I have never gotten any of those. Unfortunately, I was able to get some of these IN-8-2 tubes, which have very nice digits, and at the time were quite reasonable in price, although they seem to be going for more like about $15 compared to the $2 or $3 I paid back 10 years ago. So the circuit will work pretty much with any Nixie tube, with maybe some adjustments on the anode resistors to adjust the current. But so it's a very flexible solution if you get his modular approach that's similar to what I've built on the board here. If you get the all-in-one, of course, it's pretty much dedicated to a specific tube type, which you need to obtain off of eBay. And the prices on these things are only going up. So if you're thinking of building one of these, it's better to jump on it now, because I had for example, some giant alphanumeric B7971 tubes made by Burroughs back in the 70s. And I think I paid $25 for these about 15 years ago. And I sold them for probably $200 each just recently because the clock I had some issues. So those things have gone up tremendously. I don't see the Nixies doing exactly the same thing since they're more available and were made in greater quantities. But, you know, nobody's making these anymore. And we have the Soviet Union to thank for keeping these things in service in their submarines and military hardware for so long that even date codes as recent as 92 or 93 are present on some of these that date to the dissolution of the Soviet Union itself. So these were into production right up into the end of the Soviet Union era back in the early 90s. Very cool. So anyway, home bell clock, Ian Sparks, check him out on the web.